That's one half. So we have shown that sigma 2 is solvable by NP to the SAT. NDTM given another NDTM as an oracle, right? That's an interesting thing. Now the other half is showing that NP to the SAT can be written as there exists for all. So let's do that. So NP to the SAT is in sigma 2 part. Let L be in NP to the SAT. Decided by poly time NDTM n using SAT oracle. So this n will make choices, right, non-deterministic choices, and will also refer to SAT. And this whole business we have to express as sigma 2 expression, right. So this we have to do carefully, and we'll obviously also use Cook-Levin here. So n makes choices in its execution path and queries the oracle on CNF formulas. So the choices intuitively will refer to there exists quantifier, and the queries, that analysis will be more will be trickier, right, because querying for SAT, right, the query that is happening is for SAT problem. So answer may be yes or no. So yes will correspond to there exists quantification, and no will correspond to for all quantification, right, SAT complement, and we have to keep track of that separately. So let's study an execution of n on x. Okay, so say n makes bit choices C1 dot dot Cm. So that's the non-deterministic choice. Remember, in an NDTM, in every step there is a choice which transition function to use, delta 0 or delta 1, right. So that is what C1 to Cm represent. And say n queries SAT on formulas phi with these choices accounted for, that this is the first formula, then second formula, and finally key formulas. And gets answers E1, E2 dot dot EK, which are bits. Right. So these are the important things in the computation, in the execution path of n with input x. So the bit choices which were made by the, in this particular execution path C1 to Cm, what were the SAT instances queried, that is phi1 to phi k, and what were the answers obtained respectively A1 to AK. 0 answers will correspond to SAT bar for all quantifier. 1 answer will correspond to SAT, there exists quantifier. Okay. So then what do you get? So now X is accepted, it's a yes string if and only if there exist choices and there exist answers on which n accepts. On the path C1 to Cm, and A1 to AK are the correct answers. Right. So X will be accepted, will be a yes string for L, and remember L was NP to the SAT to begin with, right? So it will be a yes string if and only if there is a way to choose the non-deterministic bit C1 to Cm. And get correct answers A1 to AK, such that with this information, this is the only information n needs, everything else n is deterministic. So given these two things, then n accepts on the path, right? That is exactly the definition of yes string, which we can now write in a different way if and only if. So the thing is, how do you verify that A1 to AK are correct answers? Right? For this, we have to go back to the definition of SAT and SAT complement. So that's what we will do. There exists C bar, then there exists this A bar, A1 to AK. There exists U1 to UK, such that for all V1 to VK, so U1 to UK is comes with is quantified by there exists. So this will be used to check those answers A1 to AK which are 1, and V1 to VK will be used for those answers that are 0. Let me write it down here. Okay, so it's for those answers to check whether they are correct or not. So n accepts X on the path C bar and answers A1 to AK. Path C bar, oracle answer A bar, and now the verification, the correctness of the answers. So that is for all I in K, when AI is 1, when AI is 1, then there should be a certifying assignment. Okay, so UI is the certifying assignment, and the same for all I. When AI is 0, then phi Vi is 0. But note that VIs are quantified by for all, right? There is a for all on VI. So that's a different demand. So VIs, every VI, it should come to 0 if the answer AI was 0, while UI is quantified by there exist. So UI is quantified by there exist, VI is quantified by for all. Right, so that is why 2 quantifiers are needed. That is enough to check the answers, and finding the path, the non-deterministic bits, that for that there exist is enough. There exists C bar, and this you can see is already a sigma 2 expression. So that's what we deduce. So we deduce that L is in sigma 2, right? Which means that NP to the SAT is in sigma 2. And we have already shown that sigma 2 is in NP to the SAT. So they are actually equal now. So NP to the SAT is sigma 2. NP to the SAT is also equal to NP to the NP by definition. Okay, so that's the structural result. The structural result says that sigma 2 is NP to the sigma 1. And yeah, so that finishes the proof. The remaining stuff I leave as an exercise. So fill in the details for I greater than equal to 3. Okay, this will be identical. The proof will be almost unchanged. You just have to be more elaborate with the quantification, and then by induction this will be proven for all i's. Basically, you have to design this. You have to show that sigma I, there is an NDTM which is using sigma I minus 1. Now sigma I minus 1 again has answers. Query answers can be yes or no. Yes will be sigma I minus 1 SAT, and no will be pi I minus 1 SAT. Okay, so SAT and SAT complement, and then yes no answers you verify separately as we did just before. Okay, so what we have shown is that sigma 2 is NP to the NP, sigma 3 is NP to the NP to the NP, and then it becomes hard to write this, just a tower of INPs. Okay, so this looks pictorially better than the first definition of polynomial hierarchy. Okay, this is the hierarchy. Keep putting NP in this tower. And the open question here is that NP raised to NP is conjectured is harder than NP. Okay, though P raised to P is P. So P raised to P you can show easily is P. It's basically because you can negate within the class P, negate the answer of the query within polynomial time. That you are not able to do in NP to the NP. Okay, you are not able to actually negate the answer within NP. So it's the same NP co-NP difference. If NP co-NP are different, then this question is resolved. If NP co-NP are the same, then actually NP to the NP. Yeah, so then what happens? Think about that. So what happens if NP is co-NP? Okay, basically you have shown that polynomial hierarchy collapses to NP. So sigma 2 will become NP in that case. So what we'll do next is what we'll now investigate the space between the polynomial hierarchy and P space. Okay, so again we don't really know whether these two are separate, but under all this theoretical evidence, it's safe to say that PH and P space are PH is proper subset of P space. So can we now fill that gap? Talk about that gap. Is there something interesting in that? And indeed, there is a very interesting complexity class, or many complexity classes that we can put there. And that brings us to the topic of counting. Okay, so let's study the complexity of counting problem. So the main motivational problem is sharp set. So it maps Boolean formulas to their number of satisfying assignments. Okay, so it will map this function. First of all, it will sharp set will not be a decision problem, it will be a functional problem because we want to count. And the function is map phi to the number of satisfying assignments. So number of satisfying assignment of phi. Okay, that is what this functional question is. And as always, our interest is how fast can you solve this. So is sharp set efficiently computable? Okay, so what is the, I mean, we need to define a complexity class which covers functions instead of decision problems. So P is for decision problems that can be efficiently solved. FP will be for functions that are efficiently solvable. Functional polynomial time. So FP is f such that this function on the Boolean strings is computable by polytime Turing machine MF. Okay, so it's similar to P except that the elements we are talking about are actually functions. Okay, they don't output a bit but many bits, output a string. Call it functional polynomial time. And now we formalize the question. Is sharp sat in FP? So given a Boolean formula, can you count the number of satisfying assignments in polynomial time by a deterministic Turing machine? And the conjecture is that you cannot, right? If you cannot, if you conjecture that P is different from NP, then you can't check satisfiability. So there is no chance that you can count the number of satisfying assignments. Right? Even distinguishing 0 from non-zero, we assume is hard. So clearly that's the conjecture here also. And so the first counting related complexity class is sharp P. So sharp sat motivates the class sharp P, which is formally defined as, so function f is in sharp P if there is a polytime Turing machine M and constant C such that for all inputs What is f of x? F of x is the count of the number of satisfying assignments of some NDTM on the input x. Okay, so f of x is equal to the number of satisfying assignments, let's call it y, which will be, which can be polynomially longer than x, so x to the c, just as a formality, mxy equal to 1. So it is counting how many y's are there that satisfy Turing machine this verifier m's computation. So it's also that. So we can write it like this: sharp P is the collection of functions that count the number of accepting paths of an efficient NDTM. Okay, so sharp P always, any problem, any function in sharp P has this property that it's a counter for a polytime NDTM. Okay, so f on x will be the value in how many ways is the NDTM accepting x. That's a natural thing, although P here is kind of misleading because we don't believe this sharp P to be efficient at all. Okay, in fact, we believe it to have very hard problems. So this sharp P is not like P; it's more like collection of NP hard problems or harder. So, anyways, we will see how hard it is later. Right now, let's just list some immediate properties. So, first is that sharp SAT is in sharp P. Why is that? Well, sharp SAT was defined as number of satisfying assignments of a Boolean formula, and a satisfying assignment of phi is basically just an NDTM making choices. So that NDTM's number of accepting paths is being counted, right? So that by definition is in sharp P. It's a problem in sharp P. It's a function in sharp P. And next is even more trivial, functions that can be computed in polynomial time, they are in sharp P, right? Because here these are deterministic Turing machines, so you don't even need the non-deterministic bits. So open question here is whether FP is not equal to sharp P. Okay, just like this is the counting version of P not equal to NP. Okay, in a way, if you want to show that P is not equal to NP, then this also you have to show. This is implied by P different from NP, right? Because if Contrapositive is if Fp is equal to sharp P, then clearly P is equal to NP. So this is something that you have to show if you want to show P not equal to NP. And how is NP and sharp P related? So although we feel that NP is much easier, but comparison we cannot do directly because NP has decision problems, sharp P has functions. So instead we write it like this. So if you are given sharp SAT oracle, then by a polynomial time Turing machine, using that oracle you can solve SAT, right, trivially. So NP is in P raised to sharp P, and this whole business can be done in P space. So here we are allowing sharp P as an oracle, so functional oracle, right? And sharp SAT is in P space because in the same space you can actually just enumerate all the satisfying assignments. So these are the basic properties.